Let's talk about inductive bias, just for a bit. What is it? Let's start with some examples. So, there's something called page shyness that was observed in rats. Basically, we are building learners, and it will be good to turn our attention to how animals learn, or other successful learners. Remember, according to Wikipedia, learning is possessed by humans and animals only. So a rat, when it encounters a new food, it's been observed, it tries a little bit first, and then kind of watches itself, waits. If it becomes nauseated or something's like it doesn't feel well, it never touches that food anymore. So basically, there is a learning process here, sort of trial and error, and before they start eating good quantities of food, they try to avoid poisoning by bad food, so they try eating a little bit. But let's watch that. Another animal.
Like most living creatures, the pigeon quickly associates the pressing of the lever and the reward. But when a timer releases a seed automatically every 20 seconds, the pigeon wonders, what did I do to deserve this? If it was flapping its wings at the time, it'll continue to flap, convinced that its actions have a decisive influence on what happens. We call this pigeon superstition.
So rats try a little bit of food and then make conclusions about their food. Pigeons, in this video especially, they also try, they also strive for food, right? But they observe instead of actively trying to do something. Although they're smart birds. They can press a button, as you've seen in this video, to get the food, or they can move a box to sort of control their height to get to the food. But the main point is both of those animals, rats and pigeons, they practice something called inductive reasoning. Inductive reasoning, you all know proof by induction, right? When from small local points or from small local dependencies, assuming that nothing changes further, you can establish that if something holds for a base case, and then it holds for every step, every transition, then it holds forever, everywhere. So inductive reasoning in rats is similar. If they tried food and it made them feel bad, they kind of assume, or the learning process forces them to assume that this kind of food will always be bad for them. Or reverse, if they try food and the food is something tasty, good, doesn't make them feel bad, it becomes the familiar food, and they make an inductive step that this food will always be good. So with pigeons, the story is slightly different. The pigeon superstition, it's the pigeon starts doing more and more of the stuff that they were doing when the good stuff is happened to them. So they observed correlations, and they try to reinforce the effect by just following the correlations that observed. Let's watch another video from the father of behaviorism, who observed this behavior in pigeons. Skinner.
We'll just watch its behavior a bit. It's not doing anything in particular, you see, but I'm going to try to get it to do something. Suppose I shape up the behavior of making a complete turn. What I do is simply, as I did then, to wait for some part of that behavior. There's more of it, you see. You can see the effect is instantaneous. I'm waiting for it to turn counterclockwise now. And then I reinforce that movement. And I wait for a more pronounced movement than that. It's got to be more than that. There we go, all the way around.
So the point is that by reinforcing, by adding immediately, by the way, adding some kind of conditioning, Pavlovian conditioning, the bird can be made to do some interesting tricks or whatever B.F. Skinner wants the bird to do.
Now we'll just watch its behavior a bit.
Okay. Apologies. Let's jump here. So what about rat superstition and conditioning? Can we do that to rats with their foods? So when they try some food, can we electroshock them and make them not like that food and avoid their food? Yeah, we have lots of things that we can torture them with, and the saddest evil people in the lab codes have done that all, right? We can make loud sound, sudden loud sound, we can splash them with water, or we can whatever, electroshock them. So the goal is to induce negative conditioning. So they try some food and it's tasty, but you get electroshocked. So what the researchers observed doesn't work. Only if the rats are like they have food poisoning problems, like nausea or any other problems with their food tract. Only then they negatively associate the food with the being poisonous. But otherwise, they continue eating it even if it was causing them bad feelings or bad something bad that the researcher has done to them. So interesting. Pigeon practically overfeeds, and a rat in this particular example does not overfeed. So can we do something? Can we learn from those two animals? Well, actually from a rat. In our case, what can we do so our learner doesn't overfeed the hypothesis or the classifier? So one solution, and the solution we'll consider today, is search over a restricted search space. We will choose a hypothesis class in advance. Instead of a learner picking up any possible age, any possible classifier that satisfies or minimizes empirical risk, we will say, okay, only from this particular class, select an predictor, age, that minimizes empirical risk. Give me a second. Yes. And then, in this way, we introduced inductive bias by biasing the learner to a particular set of predictions, but we want the learner to learn predictors such that they will perform better in that inductive reasoning on unseen samples. That's why it is called inductive bias. So there are other inductive bias here, of course. We could say maximum conditional independence cast in a Bayesian framework. Try to maximize conditional independence. That's an inductive bias, and naive Bayes, which we will cover in this class, uses that. We can use minimum cross-validation error. That is also an inductive bias. That helps, well, it's a bias, it's not a guarantee, neither of them. We can use maximum margin inductive bias. We will cover that in this class as well. You will understand what it is. Minimum description length, MDL, maybe, but that's another inductive bias that we can impose, sort of an Occam's razor. And minimum number of features, for example, and nearest neighbor, another inductive bias. So lots of possibilities for improving the learner. But for now, let's say that finite hypothesis classes, what will help us to avoid overfitting. And it does. It's an inductive bias that helps us avoid overfitting.